These quasi-particle excitations are a nice setting to, oh, sorry, resuming my screen share, are often a nice setting to explore the interplay of symmetry and topology. So two kind of canonical examples are that if you have a broken symmetry, quite often topological defects are sort of natural quasi-particles of broken symmetry state. So it's fruitful to think of them as sort of particle-like excitations and work with those as low energy degrees of freedom of the system. And conversely, one of the signatures of interacting topological phases, very often a striking signature, is that quasiparticles have fractionalized quantum numbers. And that's a signature of an underlying topological state of matter, famously in the fractional quantum Hall effect. So what I'm going to do today is give you explore two of the simplest examples of how broken symmetry and topology can affect quasiparticles. So the first part of the talk, which will be more or less the majority of the talk, I'll focus on the simplest example I know of an interesting broken symmetry quantum phase, which is the 1D quantum Ising chain, and talk about its domain wall and spin flip quasiparticles. And in the second bit of the talk, if I get time, I'll talk a little bit about excitonic physics in integer quantum Hall states, but in the setting of Moiré heterostructures. So the first talk is about a material which is cobalt neobate, CoNb206. And so jumping right in, this is a material which forms naturally a triangular lattice of 1D zigzag paramagnetic Ising chain. So it's a material where the copper 2+ ions host a non-Kramers doublet, and they form these zigzag chains that run basically along the C-axis of this material. And these zigzag chains are stacked in a triangular lattice in the AB plane with very, very, very weak interchain couplings between them. So to a leading approximation, you can think of each zigzag chain as being described by the biggest terms in the model are a nearest neighbor Ising coupling, where J and J+1 are nearest neighbors along the chain, and a term where I'll flag this because based on some crystal symmetry nomenclature and to be consistent with the extant literature on this, I'm using a slightly unconventional representation of the Ising symmetry. So the Ising symmetry is a flip generated by e to the I pi sy. So it's a flip about the y-axis by 180 degrees rather than the usual thing is the x-axis. And so the second term that's important in the Hamiltonian is an applied field that can applied transverse field. And so this is the famous transverse field Ising chain Hamiltonian. But the interchain couplings between one zigzag chain and say another zigzag chain nearby essentially have to be accounted for. And the way a very good way to account for this that matches experiments pretty well is to just think of the interchain couplings as generating an effective field that, so when a chain orders, it gets some non-zero expectation value for Sz, and that acts as a mean field on the neighboring spin. So you sort of treat the interchain couplings at a mean field level, but treat the intra-chain physics sort of fully quantum mechanically as you would to study the transverse field Ising chain. So if I forget about this Hz term, the transverse field Ising model is the simplest quantum critical point in many ways, arguably the simplest, and it has a critical point in this problem tuned by Hy. When Hy is very big, the dominant, we can ignore this term largely and just think about the fact that the system wants to align along the field direction. And so the excitations are, the low-lying excitations are when a single spin flips to point opposite to the field. So the quasi-particles in this regime are naturally spin flips. In contrast, when Hy is small, the Ising couplings dominate, and you have a spontaneously broken symmetry in the absence of Hz in this problem. And you have a set of domain wall quasi-particles in that theory. The reason that these are slightly different is notice that a single spin flip is actually a pair of domain walls. So if I take a Ising spin and flip, if I point all my spins point up and I flip one spin to point down, I've actually created two domain walls where the spin goes from up to down or down to up. For the leading Ising model, there's no energy cost to separating those things out to arbitrary long distances. So the domain walls are actually nice, simple excitations of the system. They are the lowest lying excitation because a domain wall has one bad bond, whereas a single spin flip has two bad bonds that are unhappy. So a domain wall is the lowest energy excitation of the system. And there's a quantum critical point where we expect universal signatures of quantum criticality at 0 temperature and a sort of plethora of finite temperature scaling that's associated with this critical point in the quantum critical region. And this is a critical point governed by a gap closing transition. In the presence of these interchain couplings, the story is slightly modified. One important thing about the interchain couplings is also a 3D Ising, a finite temperature 3D Ising transition, because it's honest to goodness three-dimensional material. But that won't be very important for what I have to say. So largely for this talk, you can imagine that the model is governed by this Hamiltonian, except that once you go into the ordered phase, you have to remember that there's a longitudinal field that also acts on it. And that longitudinal field is a consequence of there being essentially interchain couplings, but it's just captured at this sort of simple mean field level. So experiments on this material, the simplest, the sort of natural experiment that can look at it is to look at the excitations via inelastic neutron scattering. This is sort of a well-known, this has a long history. And what this probe measures is essentially look at the dynamic spin structure factor, which basically is the 2-point correlation function of spin flips. So you act with a spin operator at site J, and then measure another spin operator at site I at some later time. But what you naturally measure in the end is the Fourier transform of this response in space and time. And so that's the natural observable that you look at. So what do you expect to see? In the disordered phase, an operator like Sx, for instance, can create a spin flip, or Sz can create a spin flip because the spins want to point along the y direction. So Sz can flip a spin from pointing the plus y direction to a minus y direction. So since spin flips are good quasiparticles, we expect to see a sharp mode in the structure factor because you couple this correlation function is in some sense naturally creates, is the natural correlation function for a quasiparticle in the system. And since a quasiparticle has a sharp energy momentum relation, I expect to see a nice sharp branch of excitations. In the ordered phase though, imagine I send in I flip a spin with spin polarized neutrons, I flip a spin. A spin flip costs energy 2J, but in fact, a spin flip can decay into a pair of quasiparticles. And it can decay into a pair of quasiparticles in many different ways because given a budget of K and omega, I can parcel out that budget of K and omega to these two quasiparticles in a variety of different ways. So a spin flip is not a stable excitation. So since what I'm measuring is the 2-point correlation function of spin flips, what I'll see is something very diffuse because a spin flip is unstable to decaying into the 2-particle continuum of these domain walls. And since in 1D, the domain wall is a place where you go from up to down, it's often referred to as a kink because of an analogy with the physics of solitone. So I'll call kink because it's just a shorter thing to say than domain wall each time. So a spin flip is 2 kinks. And so what you see is a diffuse continuum. And if you look at the data, that's actually quite nearly what you see. So in the paramagnetic phase, you see a nice sharp branch of excitations. Near the critical point, you sort of see some structure, but you still see some diffuse physics. But what maybe I want to draw your attention to is well into the magnetically ordered phase at low fields, you see there's some sharp physics here that I'll mention, but mostly you see a very broad diffuse spectrum, which is a signature of these spin flips decaying into quasiparticles. So this was some really beautiful neutron scattering experiments done by about a decade ago. But the really interesting physics that you can probe if you do the experiments and look at even finer resolution is that if you stay far away from the critical regime, so if you're relatively deep into the ordered phase, sorry, let me just reload that slide. If you're relatively deep into the ordered phase, you see in this regime, but you keep going to lower and lower transverse fields. I said that there's an interchain HZ coupling. There's this interchain field that's the effect of a neighboring chain on a given Ising chain. So imagine I try and create a quasiparticle. So I flip a spin in one chain. I flip a specified spin. It's very unlikely for me to ever get enough spectral weight into the system to flip 2 neighboring chains. And every chain is surrounded by 6 neighbors. So typically when I flip a spin, its neighbors haven't flipped in a correlated way. So its neighbors have some orientation. And because of the interchain couplings, they all agree on an orientation. The effective interchain coupling is ferromagnetic. They all have the same orientation. So the flipped spin in, say, the central chain surrounded by 6 neighbors is now going to see an effective confining potential, because if I try and grow this string of flipped spins when the domain walls try to move apart, I'm actually going to make a bunch of interchain couplings unhappy. And you can just model that by this HZ field. If you have a longitudinal field in an Ising model, you get more and more energy when the domain walls try to move apart. And that's actually a very simple quantum mechanical problem. It's a problem of two particles that move in a linear confining potential. And you can actually solve it with some phenomenological effective mass for the two particles and just do two particle quantum mechanics with it. And that gives you a spectrum of bound states that have a dispersion that's the dispersion of the center of mass. And the sort of different bound states have to do with the quantization of the relative motion. So if you think of the relative problem, it's just some airy function type solution because that's the solution to the 1D Schrodinger equation in a linear potential. So in fact, these beautiful experiments done 10 years ago so this is the data shown at 0 transverse field with an effective longitudinal field that's put in to model the data, but this is sort of in good agreement with what you expect from the magnitude of interchain couplings. What you see experimentally is this set of kink bound states. Near pi moment, there's some additional physics that comes in to do with exactly how these quasiparticles talk to each other, and the fact that there's a Brillouin zone in the problem matters, and you actually get a stable kinetic bound state. There's some extra structure here, which you can think about, but it's not particularly important to what I have to say. The key thing is this sort of airy function picture is sort of valid near k equals 0, where you really see that you get a spectrum of internal modes. It looks really like what you'd expect for the center of mass motion of some two particle atom with a bunch of internal levels. That's really what you're looking at. And often people refer to these as meson states because you have two quasiparticles that are being bound by linear confining potential. It's an analogy with what you see in particle physics of mesons, but that's just as so this confinement gives you these bound states. And what I'm showing you here is that the color map here is what you get from this toy airy function calculation I told you with some additional physics to capture the zone boundary effects. And the dots are experimental data. So the reason this paper, it's nice, it confirms Ising physics, but there's a really spectacular prediction that was made as you approach the critical point. So the data I just showed you was data far from the critical point, deep in the ordered phase. But this model, because this HZ that I gave you vanishes so the HZ is an interchain coupling. So once I go into the paramagnet, HZ goes to 0 because there's no mean field once you're in the paramagnetic regime. So as I approach the critical point from below, what I'm essentially moving towards is a Ising critical point, which in 1+1 dimensions is described by conformal field theory, with a small perturbation that takes you away from criticality based on what people would call the thermal perturbation, and a small symmetry breaking perturbation away from criticality. The HZ perturbation is small because it has to vanish once you go into the disordered phase. It turns out that the asymptotic limit where these two detunings from criticality are asymptotically small is an integrable quantum field theory that was sort of understood by Zamolodchikov in 1989 and then followed up by Fonseca and Zamolodchikov about, I guess, several years later. And the key prediction was that this mesonic structure gets an emergent symmetry that's related to an exceptional Lie group called E8. And so what that tells you is a rather spectacular prediction. It says, if you looked at the masses of those mesons in the quantum field theory calculation, there would be a set of masses and you can exactly predict the masses M1, M2, M3, M4, and so on. And the key thing is that the ratio of the mass M2 to M1 is the golden ratio, which is kind of a rather unusual thing that it shows up in an calculation. But the amazing thing from our point of view is if you looked at the picture I told you earlier, we had these modes that looked something like this. Well, if I think of the p squared over 2m dispersion, I can think of it as coming from something that looks like this picture is like something like square root q squared plus m squared. And this physics is really, this mass over here is really these meson masses. So if I look at the q equals 0 values of these dispersions, I can read off this meson mass spectrum. And this is what Radu and his colleagues did. So they take a line cut through their data at 0 wave vector, and then they look at these masses, and what they see is that as you approach the critical point, you get very close to seeing this golden ratio. So the critical point is somewhere over here. They can't quite take the data all the way there. It gets very hard to resolve these branches, but you see that there is something that looks very much like this golden ratio coming in. So in that early data, sorry, Matt, you had a question?
Yeah, this may be too technical, but can you remind me just why does E8 come up here? I mean, E8 is, I think its lowest dimensional representation is like 248 dimensional. So how do the masses somehow come from?
I don't have a crisp understanding of this E8 structure. It's not so important to it just turns out to be a feature of the Ising. The important thing is you can't get it from the lattice. It's really a special feature of taking the continuum limit and then taking the Ising conformal field theory, not the Ising lattice model. You wouldn't get it.
Yeah, okay.
So
yeah, I mean, you can get it from the non-abelian bosonization, I think. You can represent the Ising model in terms of E8. I just never understood because, you know, all the representations are highly dimensional or very high dimensional and somehow these masses come out. But okay, anyway.
It's not as important to my talk. I think the one thing I want to take away from it is, I think the important point to take away from this is it's a very, very, very stringent test of Ising criticality to see this kind of spectrum. Because you don't really expect these kind of numbers to come out of anything but some solvable critical point. So this is sort of evidence that whatever you're seeing something deeply linked to Ising critical physics, right? So there's that piece of physics. So it seems like it's a solved problem, but there's actually two puzzles. Yeah, sorry, go ahead.
So, well, your graphs disappeared there, but you have this two-particle continuum, right? You have this two particle. Is that seen in the data? Should I see that in the data? You know, I might have expected.
If you see the data, what you see is you'll see the 2M1 continuum, and that eats up the other data. So it turns out very recently some group has reported terahertz optics where the backgrounds are slightly different. So they start seeing the 3M. Sorry, I think I might have lost my screen sharing. 1 sec. Just give me 1 second to share my screen again. My keynote seemed to have died a bit. Very good. And let me share that screen again. Can you see the screen now or no?
Yes, we can.
Oh, good. You can see my talk again. Very good. Sorry. So if you go back, I didn't show you the data at criticality because I'm not going to spend much time on it, but you can actually see that only 2 peaks show up and then you sort of see the rest of it. You can sort of see the 3rd peak here just a bit, right? You can just about make it out, but it's very hard to see M3 down here. You can maybe see it, but now terahertz, very recent terahertz data seems to see it. Optics sort of seems to see the same thing now.
I see, but I don't see a very sharp turn on of that. It all just looks kind of smeared into the background. Is that expected?
You should see. I think that's not particularly great. I think it's partly because it's not the the data is great, but it's done with some error bars. You're right that you should see something more thresholdy effects, and I think the optic sees it a little bit better now.
Okay,
but it's again hard to separate against the background. I think is partly why.
Sid, could I ask you to make the screen full screen? Right now we see it a bit sharp.
Oh, okay. I'm not sure why. Let me just open it up in a slightly, I think I have to play it within a window for it to show up as full screen. So let me just open it up and start the slideshow within a window. Sorry. Okay, and let me share my screen again. Is that better?
Yes, that is better. And Sid, one very quick question. If you do the sort of classical, not a classical, but a classic quantum mechanical calculation you showed us earlier, deep in a ordered phase, you get an infinite tower of states, right? So how should one envisage going from this infinite tower of space states to being only 8? Does it mean that the rest blend into continuum?
I think the only 8 is a special feature of the scaling limit of the critical point and so on. But the fact that you have a finite number just comes in because on a lattice you have a bandwidth effect, so that's where you get a finite number out of things on the lattice. That's I think the basic point there.
Okay.
So yeah, if that makes sense, right? So that's where the lattice effect comes. That's where the finite number comes from, and that's actually required also to get this kinetic bound state and so on. So sorry, this slide came back up, but the 2 puzzles that have remained is that, so this is getting to the point I was going to say, is this dispersion. In order to get this kind of physics, you get this mass by solving a problem, and then you get a reduced mass for the, you get this kind of motion about the center of mass, and this is the problem that one needs to solve. But you see that to get a mass for these kinks, they must be dynamical, right? So they have to actually move, otherwise you don't have a kinetic energy. And the leading Ising model, in this model, where this comes from is the SY term. That's where the kink dispersion is entirely due to this SY term. right? If you go back and take your Ising model, this is what hops a kink, one of these domain walls from left to right. But the data I showed you over here with this nice spectrum is actually taken when the transverse field has gone to 0. And you see that it's not that the kink stops hopping, it's got a decent dispersion. So it's telling you that there's some kink dynamics that remains. So this leading Ising transverse field, Ising Hamiltonian, can't possibly explain the kink physics. Right? So people have tried to explain it by saying, okay, maybe they put in a phenomenological field, but if you ask Radu, do you have a field on your sample? That's a pretty good yes/no question. And the answer is there is no field on the sample. So yeah, there's a question of why do the kinks move in the absence of any terms that move them around? That's the first question. The second question is, if you go into the paramagnetic phase where the quasiparticle should be a really good excitation, the spin flip, what you see is if you looked at this dispersion at large fields, you actually see something where there's missing spectral weight. It's as though the quasiparticle ceases to exist for some part of its life. Now, this loss of spectral weight of a single quasiparticle mode at some particular wave vector in the Brillouin zone is something that people know. If you have a theory with lots of quasiparticles, it could be that at this particular point in momentum, it becomes favorable to decay into some other quasiparticles. This is a problem that you could imagine. And this is typically what happens when a quasiparticle enters the two quasiparticle continuum because of the singular density of states at the edge. And this is something that many people have explored. But there's a wrinkle in this explanation, and the wrinkle is the following. So if I want to think about this calculation, I have to take all the particles in the theory. The only quasiparticle, this is the simplest theory I can look at. It's a field-tuned limit of the Ising paramagnet. There is really only one branch of quasiparticle excitations. It's just the single spin flip. So this object needs to decay into its own two-particle continuum. Well, you can do that. You can take this dispersion, construct the two-particle continuum of that dispersion, and ask what does it look like. And so the two-particle continuum looks like this. And this is the same. So this is literally doing that calculation. It's saying, let's give you some energy and momentum. And when is it possible to build up that energy and momentum? How many ways can I take that energy and momentum and parcel it into two quasiparticles that are controlled by this black line dispersion? That's the calculation that you do. And you get a picture like this. And you say, these two things touch and it's in the ballpark. Okay, we're done. Except for a single spin flip to decay into two spin flips, you need to break Ising symmetry. And also, if you look at it, it turns out that I drew this picture and I reproduced it from a paper which proposed this explanation. If you change parameters even slightly, these things stop touching. But here I just swept a field through 2 Teslas, which is pretty large on the scheme of things, deep, and moved through quite a large swath of the paramagnetic regime. And the decay seems robust and evolves. If you notice, this isn't at some particular corner wave vector of the Brillouin zone. It's actually moving to higher wave vectors as you evolve. And if you try and do the same calculation here, roughly speaking, what a field does is move the bottom of this minimum up and moves this gray area up by about twice as much, because this is 2 quasiparticles, this is 1 quasiparticle, so they couple to a field with roughly a ratio of 2 between them. And you'll see very quickly that these two things stop talking to each other, and so this decay becomes much more difficult to explain. So basically, sorry.
The yellow part? What's the yellow part? I mean, that's showing crossing to. I mean, is that another excitation?
Yeah. So it's not another excitation. So it turns out that that yellow part, great question. So that yellow part is actually a little bit of a clue towards where the answer comes from. So the yellow part turns out to be a shadow mode based on the fact that my wave vector is not perfectly aligned with the, I'm saying that I'm plotting this as a function of k, but it's actually, and I'm thinking of it as a 1D system, but actually that wave vector is slightly misaligned from the axis. So it's picking up a mode that's going in the other direction that isn't really there. It's just a kind of symmetry effect, and I'll explain where it comes from. But you shouldn't think of this as, notice that this thing just stays, it's a reflection of this. So this could be an explanation if it was crossing at pi. This mode actually this yellow mode always crosses the darker area at pi. But if I can show you what this thing will evolve to at higher fields, and it'll be well away from pi. So it's not an explanation of what's going on directly, but the physics of why this mode exists is actually related to, why do you see this weird shadow is related to the actual answer. I hope that helps. And you'll see the thing in a minute or two. Is that okay?
Yeah, sure. Yeah.
Okay.
Sid, what happens to this feature when you approach the critical point?
That feature is always there. The way you can tune that feature, make it stronger or larger, it's not to do with the criticality as per se. If you rock away from the, so at the critical point, things look quite painful, but you won't see anything from the paramagnetic side. It's really a symmetry effect. It's to do with the fact that if you're in a truly 1D regime, there's some extra symmetry in the problem. If your wave vector is aligned along the crystal axis, and if you slightly misalign, you see an echo of it from another from a different sort of symmetry. It's basically your probe is breaking a symmetry that's there in the model, if you like. That's basically what's happening with that shadow mode. So one way you can see that is if you rock your wave vector, that shadow mode amplitude goes as cosine of the angle, or sine of the angle between the actual way, between the c-axis and your k that you're actually scattering off of.
But 7 Tesla is still some distance away from the transition.
You're way into the critical point here. Yeah, this is nothing to do with the transition. You're deep in the ordered phase. Yeah,
okay.
The transition is about 5.5 Tesla.
But around that field, you're saying this feature still has some remnant? Or
This feature has no dependence on field. It's just sort of sitting around. It has dependence on angular misalignment, but has almost no field dependence. It's really just a shadow. It's well understood. It's like it's an experimental. There are papers and papers written on this. If you want, we actually have a beautiful explanation of it, and we can reproduce it perfectly numerically. Like we can give you, you give us an angle and we can show you an exact amplitude for this mode. We don't do it because it looks a bit ugly, but we understand it completely. And I can tell you it has nothing to do with the criticality and directly.
No, but maybe I was not being clear. So this special K that I was not referring to the yellow.
Oh, okay, sorry.
Yeah.
The K star, the point is that the K star appears at so it's not universal physics, so it has nothing to do with criticality. It has to do with when the 2-particle continuum and the 1-particle continuum overlap. So there's some accidental parameters that go into that, right? It's not a universal thing. So by the time you get to the critical point, there isn't big evidence of quasi-particle breakdown, because in that regime, the 2 continua don't overlap significantly in the way that they need.
And just in the K space, the one doesn't see much of anything.
You don't see this. You don't see much of this there, right? As far as I can tell. Yeah.
Okay,
great. They don't have too much data coming into I haven't seen so much of the data coming into the critical point from above, but from below, the structure is crazy near the critical point. You'll see why in a second.
Sure. Yeah. Okay. Thanks.
So unfortunately, I told you all the stuff that you can say from, the nice simple Ising model was all this nice critical behavior. And so sadly, we have to go into the ... that we hope never to talk about. All the stuff that you don't care about when you do when you look at universal physics is responsible for what's going on. So let me just get some stuff out of the way. A lot of physics that you have, there's some gross features like this bound state at pi and so on, that, the fact that these multiple continua were squeezed together at pi and all this kind of stuff, that needs you to invoke a second neighbor ZZ term and this kind of XY term. So this thing is required for the kinetic bound state. And this second neighbor term is because if you try to fit it to cosine K, you find it has a little bit of cosine 2K as well, just if you try to fit dispersion. So these are all just qualitative things. And they're important, quantitative things, they're important, but neither of these terms allows the domain wall to hop when you send HY to 0, nor do they allow the quasi-particle to decay. They just don't let you do that, right? So it turns out the answer to the puzzle, and if you just take a 1D chain, no other terms are symmetry allowed. You're done, basically. Any other symmetry allowed term doesn't let you do that. So my student, Michele Fava, actually was very smart. He said, well, look, if it's not 1D, then we have to break 1D-ness. And if you look at the fact that the chain is a zigzag, let's look at this and see what it does. So it's a zigzag chain. And if you actually look at a zigzag problem, then if you actually only require the symmetries of a zigzag chain, you're actually allowed a staggered term of this kind. Because in a zigzag chain, technically 2 neighboring sites don't have to be exactly the same. And if you look at the full threefold, if you try to write down a full magnetic model, you say, let all the terms be there. Empirically, the system has very small interchain couplings and very large intrachain couplings. But based on symmetry, let's write down all the possible couplings and forget in 3D. And then ask what are the allowed interchain couplings based on the full 3D space group. You get one extra term that's very special. It's and because these are non-Kramers is why you have a lot of interesting additional terms you can write down. You have a term that's staggered from site to site, so it alternates sign as it goes. And it's a YZ nearest neighbor coupling, right? So notice that it breaks Ising symmetry. And if you think about it, you can show that it allows domain wall hopping. You can just check that explicitly by just solving the low, put in two domain walls and ask, does it allow them to hop? And it does allow them to hop as, allow a domain wall to move. So one thing you can do if you have good numerics is just run a DMRG simulation with the microscopic model with this one extra term added and see how you do. So again, these white dots are experiment, but now this is not some phenomenological Airy function model. This is full microscopic simulations. Okay, you have one fitting parameter, which is just to make sure that the overall thing comes in, but that's it. And you see that we get pretty good match to the data. So we're seeing, we get very, very good agreement. There's some details here that you get wrong. Part of the reason is that what we did was only fit our new included parameter based on known values of the other things from other parameters from previous work. A more honest fit would be to do a full 5-parameter fit, but each of these simulations takes over a day to run to get the DMRG to run to this resolution. And so if you're trying to do fitting in a 5-dimensional space with this kind of thing, it's a lot of work. So this is sort of good enough as a starting point. This at least tells us we're on the right track because, earlier to get this kind of things, you had to put in a phenomenological hopping. Now we have a fully microscopic picture that gives you domain wall hopping. So it seems like we're on the right track. But there's a problem. It looks like I threw the baby out with the bathwater. And the reason is this term has two things. It explicitly breaks Ising symmetry because Ising symmetry in this problem was a product over, was a 180-degree flip about the y-axis. Under that symmetry, the sz goes to minus sz, sy remains unchanged. So this term flips sign, so it breaks the symmetry. It also explicitly breaks nearest neighbor translation because this term is different on odd sites and even sites. That's extremely difficult to reconcile with experiments. So if I look at experiments, and so here I have to get into a bit of care, I define C, let me define C the honest way as being the spacing between two of these sites. I'll define C twiddle to be a nearest neighbor spacing along the zigzag. So notice that C is twice C twiddle, right? So I've told you that the system has a unit cell of size, a true unit cell of size C. So if I was seeing that true unit cell in experiments, what I should see is a Brillouin zone that is defined as 2 pi over C. Instead, and so that's a Brillouin, instead in units of 2 pi over C, I see a Brillouin zone that's twice as big as it should be. Notice that this dispersion is periodic with the period 2 when it should have been periodic with period 1 in these units, right? So that's the zero field spectrum. That's also true. I showed half the, this is half the dispersion in the paramagnetic and the deep in the paramagnetic phase. And again, you see that it's got a bigger Brillouin zone than it should have. Does that make sense? In terms of what the problem is. So it has a Brillouin zone that thinks the unit cell is 1 lattice spacing, but I've told you the symmetry of the problem, it actually tells you that the unit cell is 2 lattice spacings in these units. That's a problem, right? And so the other thing that's a problem is that I broke Ising symmetry explicitly. And I told you that it had sharp signatures of an Ising critical point. If you explicitly break the symmetry that you're relying on to have a quantum critical point, that's a bit worrisome that you're seeing very, very sharp signatures. Because you would think that, okay, maybe it could be that you're seeing a crossover and that's there, but it's sort of quite a sensitive thing. So you might ask, wouldn't it be nicer to have is there a scenario in which they can still be a sharp critical point, even though you've broken Ising symmetry? And that seems a bit cuckoo because if you break a symmetry, where is there a critical point? So I think I'm going to try and address those. So maybe it's a good time to pause and ask if the issue is unclear to anybody. So I seem to have solved one problem. I've deepened the ordered phase at 0 transverse field. I've reproduced the fact that there's a dispersion. I correctly reproduced this dispersion, but it seems to have the wrong symmetry from what I expect. And it seems to also break the Ising criticality by adding this term. So is that,
I was saying now in the 7 Tesla data that you actually have sort of a 2 atom per unit cell now. That's why you have 2 dispersions. Did I?
No. You have 1 atom. So my statement is the following: the microscopic model has 2 atoms per unit cell, right? Because there's a staggering. Is that clear? The microscopic model has 2 atoms per unit cell, but at 0 transverse field and at very large transverse field, it looks like it has only 1 atom per unit cell. right? Because notice the axis. These are units of 2 pi over c, and I'm showing only half the dispersions. The whole dispersion has periodicity 4 pi over c. 4 pi over c is like you have a c over 2 lattice spacing, which is this distance, right? So it looks like you're seeing a smaller unit cell, which is a bigger Brillouin zone. So it looks like the model is more symmetric than it is. Does that make sense?
Yeah, sure. Yeah.
Okay, the statement makes, well, it doesn't make sense, but the statement at least should be clear. So I'm going to try and make sense of this fact.
Sid, just a thought. Could it be that the value of lambda, I'm sure you're going to tell us, but could it be the value of lambda dynamically flows to 0 as you approach critical point? And as well, could it be renormalized such that you only see the effect that you see in this delta H if you're deep in the ordered phase?
That's a possibility that you might explain, but the problem is that you also see it. So that's one way you can think of that. Maybe that could be true, but it doesn't seem. But you know, things like a symmetry breaking should not flow to 0 like that, right? You wouldn't expect this for something that explicitly broke Ising symmetry. You'd have to be more suspicious. From the point of view of symmetry breaking, this is a relevant operator, right? You're allowed to throw things away that are irrelevant unless they are charged under the symmetry that you're protecting. You're not allowed to throw this away because this is charged under the symmetry of your critical point. It's the leading, even if it's irrelevant by power counting, it's certainly not irrelevant because it's got an SZ, it flips sign under Ising symmetry. So you're not really allowed to use RG-like statements there because your fixed point is not stable. You put a relevant operator from the point of view of its symmetry charge, if you like.
Okay.
Right, maybe you can come up with some conspiracy like how things work for liquid gas or something like that, but then you might say that there should be some first orderness somewhere else around there. So that seems to be untenable, I think, as a reasonableness. It's a great idea, but I don't think it works for the reason of symmetry. So let's see if there's a different consistent explanation. And the resolution that I like and that seems to work with everything is something that's based on glide symmetry. So what I mean by glide symmetry is now I'm introducing this smaller unit cell, which I think Peng Cheng was asking about the symmetry here. So the point is that, I'm sorry, there's a couple of statements in the, yeah, it can generate something irrelevant. I think Matt said that in the chat, and that's right, another thing it can do. So a glide symmetry is a translation by the small lattice spacing. So if I you can see if I shift the system by C tilde, nothing changes. It changes the system because it sends every zig to a zag. Right, so the system now, if I shift it by C tilde, this side goes here, so that it now looks something like this, right? So that's a translation by C tilde. But if I now do a reflection, it goes back to looking like as what it does. And in fact, I should also reflect in spin space because spin transforms in a particular way under spatial transformations. If you unpack what it is, it's actually the 180-degree spin flip. This combined operation actually leaves the system invariant. It's a perfectly good symmetry of the model, this combined operation. And in fact, these kinds of glide symmetries in 1D actually are the kind of symmetries that allow you to get away with a double Brillouin zone. So it turns out, if I give you 2 sites per unit cell, technically you should have 2 bands in your problem, right? Because every time I have 2 sites in a unit cell, I should have 2 bands. But if you have 2 sites in a unit cell and you have a glide symmetry, you can either work with a 2-band model in the Brillouin zone of C, or you can work with a 1-band model in the bigger Brillouin zone of C tilde. Normally, this is not something you can do because you wouldn't have a single band. What would happen is that there would be things would open up at the zone boundary. So if you broke glide symmetry, what you would see is a picture that looks like this, and nobody would call this a band, right? You would say that, oh, there's clearly 2 bands and I would actually work with these 2 bands. And so this is the lower band and the upper band. But if you have a glide symmetry, it turns out that you cannot open a gap at the zone boundary. This is actually a very, very famous fact that goes back to the work of Conyers Herring in his PhD thesis, was constructing character tables for space groups and pointed out that glide and screw axes have this property that you can either work in the small Brillouin zone or work in the larger Brillouin zone. He called them the monodromy of bands. And this is sort of a neat fact that you actually basically, even though the symmetric unit cell tells you should work with a 2-band model, you can unfold into the bigger Brillouin zone as long as you preserve this symmetry. And sort of a deep fact of non-symmorphic symmetry is that you can do this. And so if you think about this symmetry, this sort of tells you that there's a natural symmetry in the problem that allows you to work with either unit cell. This is why the things have this smooth evolution and can fake you into thinking you have a bigger zone. And whenever the glide symmetry is unbroken, the dynamic structure factor sees the large Brillouin zone. The Ising order actually breaks the glide symmetry spontaneously. And so I'll show you that that actually leads to exactly the same critical theory. The subtlety that you don't see it at hy equals 0 is at hy equals 0, the crystal has a different symmetry, which is also of the same kind. So precisely at hy equals 0, once again, you have a nice unfolding into the full Brillouin zone, which is a very, very weird accidental symmetry. But we'll show you data at intermediate HYs in the ordered phase, which I was careful to avoid, and we'll look at the Brillouin zone of that in a second. So let me now tell you why I think it should have an Ising critical point. So Andre had a nice argument based on maybe it could be because it's irrelevant. I'm going to show you something a little bit different, which I think is I personally think is more compelling. So what I'm going to do is perform a unitary transformation on this Hamiltonian. All that means is that it's a fancy way of saying I'm just going to go through the system and flip the Ising axis on every second site. So every odd site, I'm going to flip the sign of the Ising axis. Under this symmetry, you see that the domain wall term, because I flipped the Ising axis, now becomes perfectly translation invariant, which is great. All the other couplings are translation invariant, but the ferromagnetic Ising coupling will now become an antiferromagnetic Ising coupling, because you can see that a staggering term flips a ferromagnet to an antiferromagnet. It also flips the sign of the HZ term in the problem, right? So this was the sign of HZ goes to minus HZ because, well, it staggers the HZ term. The interchain couplings now become staggered, and that makes sense because in the new basis, a ferromagnet in the old basis is a staggering in the new basis, basically. So why did I do that? I mapped the problem to an Ising antiferromagnet in a transverse field plus a staggered longitudinal field. The order parameter of an Ising antiferromagnet breaks two symmetries. It breaks the Ising symmetry and it breaks lattice translation. In this new language, the domain wall term breaks the Ising symmetry explicitly, but actually is translationally invariant. So it turns out there's a well-known fact going back, I think it was folklore for many years, but there's a nice reference to this paper by Ovchinnikov and collaborators from about 20 years ago that points out that the Ising antiferromagnet is actually stable to a field perturbation. The critical point is stable because what happens is that the Ising antiferromagnet breaks lattice translation to lattice translation by two sites. And that's a Z2 symmetry. And so the ordered phase is a spontaneous doubling of the unit cell in the antiferromagnet, which is also in the Ising universality class. And if you go back and unpack this, what it tells you is near the quantum critical point, you have an Ising conformal field theory that's perturbed by a magnetization, because now it's a magnetization is any field that couples the order parameter, but the order parameter is precisely the staggered magnetization, and something that detunes you from criticality, but that's already there. And so this actually tells you that if you just do, you can show microscopically on a lattice level that you must get exactly the same, now you take the scaling limit, you have to get exactly the same conformal field theory, and it should give you the same physics. And this is just universality at work. Except that in this picture, the Ising quantum critical point is not associated with actually an on-site Ising symmetry. It's associated with this weird intertwining of spin in space, this sort of glide symmetry. And so that's really what's going on. So why is this important? I mean, you might say, okay, fine, maybe it's just some semantic statement. It turns out, though, that this actually beautifully explains quasi-particle breakdown. So if I look at this term, let's go back to the original language. So what you can think of this term is a term that allows a spin to flip. If you think about what it does to a spin flip can go from a one spin flip sector to the two spin flip sector, but it has to do it picking up momentum pi. So if you remember earlier, I constructed the two quasi-particle continuum from the one quasi-particle dispersion. So when I want to do the kinematics of quasi-particle decay, I have to do the same thing, except I have to do it where I take these two quasi-particle branches and overlay them on top of each other with a pi shift. So basically it says the two quasi-particle sector of this dispersion is pi shifted relative to the one quasi-particle sector. And basically it's saying there's a matrix element that says you can decay, but you can only decay with an Umklapp process. So the correct kinematic matching is this calculation. And you see that there's actually sort of a nice quasi-particle decay that comes in the spectrum, that you can see these things cross. And if you go through the details, I don't have time to go into it now. If you step through the details of how this moves as you tune the transverse field, it has the right evolution. But maybe a more convincing thing is to say, well, I've got a microscopic model that I fit at 0 transverse field. Now I have no free parameters. Let me ramp up the field to 9 Tesla, just go up to what 9 Tesla would be for this microscopic model. So just follow through what I should do, and just see what my simulation would give me for the dynamic spin structure factor. And there you have it. So what you see is this very, very sharp quasi-particle dispersion that sort of qualitatively has all the features. You notice that there's some extra stuff over here. We can actually explain this. This is to do with the fact that there's peaks in the density of states inside the two-particle continuum, and there's additional structure. Experiment doesn't quite see that because the resolution isn't great over there. So there's some stuff that they didn't go to in the experiment. So it's not that there isn't. You can sort of see there's some faint data, but they didn't work very hard to extract more stuff at those energy scales. I should also point out, to go back to this question of what this cross-propagating branch was. So it turns out that if you actually look at the spin structure factor, there's some extra form factors that come in that tell you that you should see that come in when you have a scattering wave vector that is kz 0, 0. Sorry, I'm doing this wrong. So if I look at 0, 0, k as my scattering wave vector, that's what I'm pretending in all these. I'm doing a purely one-dimensional calculation when I do these numerics. In the experiment, it's actually something like 0, something like small angle theta, and there's some k minus, k cosine theta sort of thing over here. I'm actually slightly misaligned because no experiment can perfectly align you along the axes. It turns out if you put this in and do all the form factor calculations, you precisely reproduce a mode here which has the same qualitative behavior. And experiments have seen that mode also, because you can just go in the paramagnet and just force your misalignment and just fit it to a nice cosine rocking curve, and you get that to match perfectly. So you know what this extra backwards dispersion is. It's the perfect mirror image of this dispersion going back. That's all it is, if you like. So it's actually well understood, and you can see that the quasi-particle decay sort of gets fairly quantitative features right. So this is work that's in progress, but just to say that the simulation can give you some stuff that we still don't understand in sort of an effective level. We have a microscopic model, and we can park ourselves between the hy equals 0 point and the critical point. Now at hy equals 0, there's a separate accidental glide symmetry. So where, the earlier symmetry I did was do a translation by the sort of small lattice spacing and do a flip in y. It turns out when hy equals 0, you can actually do a translation and do a flip in x, and that is actually a symmetry of the problem. And if you look at that symmetry, it actually, even though the glide symmetry is broken, the dynamical structure factor is unable to probe that symmetry breaking. There's a precise cancellation of the term that would pick up that symmetry breaking due to form factor effects when you unpack everything carefully between the microscopic model and what you measure in the experiment. But away from hy equals 0, that form factor effect is much weaker. You should still see something, but you should actually see that the unit cell doubling and the Brillouin zone halving should be seen in the ordered phase. So if you actually look at the quasi-particle dispersion, you'll see it, except when I look at the spin structure factor, what you actually see is something that's gone processed through a form factor that has some structure. But you can maybe start to see here that the difference between this region and this region is really to do with form factor effects. But what you can see is that there's an underlying dispersion that's only 2 pi over c periodic instead of 4 pi over c periodic. The fact that you don't see this is a pure form factor effect. But at high fields, even with the form factors put in, you can sort of see robustly, there's no way you can ever come back to recovering this dispersion. You really have the full 4 pi over c Brillouin zone. So it seems to be that what we're seeing is that the Ising symmetry breaking of this problem is consistent with a glide broken phase. So what's really interesting is that, to me, this is a beautiful story of an example of a case where universality is really powerful, so you still get the Ising CFT, but also these non-symmorphic symmetries are actually responsible for a lot of interesting physics in electronic systems. So it turns out that topological insulators in higher dimensions and Weyl semimetals with non-symmorphic symmetries are very common, and they're kind of a natural way to get interesting physics at zone boundaries. But to my knowledge, this is the first time where they've actually shown up as a quantum critical point associated with sort of a spontaneous breaking of a non-symmorphic symmetry. So it's sort of a first example of this. And what you see is that these symmetries are really important to consistently explain things like the dispersion of these bound states of interacting quasiparticles and the breakdown of these, of quasiparticles in the disordered phase. And really this is linked to the fact that the quasiparticles in the disordered phase carry robust Ising symmetry quantum numbers, and the quasiparticles in the ordered phase, these kinks have robust sort of properties that have to do with the fact that they're these sort of quasi-fractionalized excitations in the sense that a single spin flip decays into a pair of domain walls. And it turns out in order to understand their spectrum, you really need to understand the fact that individual kinks not only carry an Ising charge, but they actually carry some non-trivial crystal momentum. And that's really why, or the spin flips again carry non-trivial crystal momentum, which is why when two of them scatter, they need to scatter all the way across the Brillouin zone. That's really important to understanding the sort of dynamics of these quasiparticles. And this is relevant because there's a lot of proposals to understand. So quasiparticle breakdown is actually a fairly interesting effect in interacting conformal field theory, as is quasiparticle confinement. And so, oops, sorry, I think I somehow managed to close the screen sharing again, but I won't. Sorry. Excuse me for a second. And let me share my screen again. Sorry about that. It should be visible again. Sorry about that. And so what I've shown you is an example of how defects carrying translational symmetry can give rich physics. I think I took a little longer time than I expected, so maybe I'll just close my talk there. There's another slides on moire materials, which are possibly also of interest. I'm happy to talk about them offline to anybody who's interested, but I don't want to, I'm conscious of the fact that it's a little bit close to the end of time. And so maybe I'll stop there and take questions on the first part of the talk at least, and maybe just close there.
Fantastic. Well, let's thank Sid again. If you were here, we'll all applaud. So I'll applaud on behalf of everybody.
Thank you.
Let's see. So other questions, and sorry, while we're working on the questions queue, anybody can submit the questions. You just raise your hand, or even easier, speak up, as long as people don't talk over each other. Sid, do you mind resharing the screen right now? We see it cut off. Like we only see.
Oh, it's cut off? Yeah, I'm sorry, why that's
it.
happening. Let me just go to Keynote again. It's somehow my Keynote is behaving a bit poorly. Let me stop my screen share and I'll boost it up again. Just give me one second.
And in the meanwhile, if anybody wanted to ask a question, go ahead, please.
Okay. And
so I don't think I can raise hand, but I'll just ask. So from DMRG, do you have something to say, Sid, about the E8 spectrum in the presence of these terms?
So it's a very interesting question. I think from DMRG, so let's first step back. I think the E8 spectrum is going to be largely the same in the sense that because it's something that came out of the critical field theory, the critical field theory is exactly the same. That was the argument of the unitary unfolding. What I think that DMRG might suggest, so I think universal physics is going to come out. DMRG gets very hard near the critical point because that's where entanglement growth is huge. So it's hard for us to do. We can do some ED. I think what's interesting is the fact that these individual defects actually carry crystal symmetry quantum numbers, which means that because of that, you might think that probes that wouldn't normally couple to them might couple to them more strongly. So one thought I had was it might explain why optics were slightly better at seeing some of these features than neutron scattering, just because it may be that they're coupling to the fact that these defects also carry something. You know, they're like solitons in polyacetylene or something in that they carry like a domain wall flip. It's also a spatial domain wall. So that could be some physics there, but I wouldn't speculate more than that. Okay. So I think there's a question from Doug.
So very, very interesting stuff. So I've been looking lately at, there seems to be a bit of a rise in literature on people injecting angular momentum into magnetic insulators via, say, the spin Hall effect. So you have some, platinum electrode on top of some magnetic insulator, drive current that way, right? And then you can have some nearby platinum electrode, and you can detect either via the inverse spin Hall effect, you can detect whatever's diffused, or you can drive a temperature gradient and detect basically the transverse spin Seebeck effect.
People talk about the spin Hanley effect and weird things like this, right?
Not even so much the Hanley effect, but I think just people have done things in fairly boring materials like YIG, right? Where you just clearly are driving magnon diffusion. And then people have done things, and with all kinds of interesting ideas about that, but people have also done things in some non-trivial materials including,
Yeah.
I can't remember which, is it a calcium cuprate? I don't know. There's a spin chain material where people have tried to look at long distance transport of angular
Cesium
momentum.
copper chloride or something? That's the classic 1D spin chain, right? There's
This wasn't, I don't think this was copper chloride. This was something else. I'd have to go back and dig out the reference. But, so I'm just curious, I mean, would one expect with the kind of complicated underlying symmetries here, would effects like that be, you know, they're really driven by exchange processes between like the spins in say the platinum electrode and the nearby surface. I mean, if the interesting excitations possess all sorts of funky symmetries, would you have a hard time coupling into them? Or
so sure, because for instance here, it's more that I think the key thing here is it's still true that even though there's this small effect, if you like, it's really a statement that things rotate away a little bit and allows these decays. It's a very small term. For that kind of calculation, I would say you should just think of it as an Ising model with the Ising symmetry, because at that scale, you're not really interested in a decay or something like that. So this weird symmetry is there, but it's a small effect, because if I turn off the term, there isn't such a term. And that term is like, I think it's about between 1/100th and 1/10th of the result. But it's amazing. If you turn it off, the DMRG data looks nothing like the experiment. So it's really powerful for the neutron scattering because of the interference that it allows and so on, because it allows certain things to happen that just wouldn't happen. But it isn't, I don't think it would be important for something like that, because you would still couple into it at some level. If you like, I'm canting is a bad word for the Ising, but roughly speaking, it's mostly a paramagnetic order parameter, but I'm tilting it a little bit because what I'm saying is that what the underlying criticality cares about the lattice translation, because formally I'm weakly breaking the Ising symmetry. But that doesn't mean that there isn't a whopping big Ising moment associated with it. It's just that formally that's not a spontaneously broken symmetry, if that makes sense. Okay. I think that's possibly the answer. What's interesting is what I'm more excited about with this material is actually the potential to couple in, do things like nonlinear response. So this is something we should be finishing up very soon. So Peter Armitage's group has been pioneering the use of doing nonlinear terahertz. And if you actually, he has a paper on this without this confining field. And it turns out, you know, the point was that he does it for the simple 1D Ising chain. So just the ZZ plus X, the classic thing that people know and love. And you do the nonlinear optical spectroscopy of that. And what you see is some signature, what you can interpret as a signature of the fact that a domain wall decays into two spin planes. But what's really interesting is when you put in these confining effects, we've done DMRG and we've played around with this, and you can match a lot of this. What you see in these 2D coherent spectroscopists like to draw double frequency Fourier maps. So their Q equals 0, but they have 2 dimensions of frequency because basically they kick the system, and then measure. So you have a time delay, a second time delay, and you can Fourier transform in those variables. And what you see here is that in the absence of these confining things, what you just see is a stripe along some anti-diagonal line. That's a classic signature of a dispersing mode in this language. But what you see as soon as you turn on these formation of these meson bound states is that you actually see side bands appear, because basically what happens is you create a low-lying meson, but a highly excited meson, but it can decay into a lower one. All these additional processes come in. So you can actually sort of see a grid, which is the full spectrum and the lifetime of one quasi-particle decaying into other and stuff like that. So it allows us to do, in some ways, precision spectroscopy of a few very strongly interacting quasi-particles, which I think is quite exciting.
Thank you.
Yeah.
Sid, I had one quick question. So in introducing this delta H term, the primary motivation was initially to explain this decay of one spin flip into the 2 quasi-particle continuum, right?
Yeah.
And it was all in the fields that were to the right of the critical point in a paramagnetic regime. Now, I remember when this experimental work by Radu first came out, there was a bunch of people who deal with CFTs at the language, sorry, the names escape me here. But so the idea was to try to do the analog of the E8 calculation of Zamolodchikov, but approximately, to try to see what would happen with the masses of those mesons, the 8 masses, when HY was finite. So imagine a phase diagram where HY and HZ are both finite, so technically you're not, strictly speaking, at CFT anymore, but there are some perturbations. So does your, either your DMRG data or experiment, could you comment on that?
Yeah, so we can show you what that looks like, right? So this was actually in that regime was exactly this. So we can certainly match the experiment. We just don't know any more microscopic understanding. This is really the regime where you're in the ordered phase, but not at the critical. So this is, you can, I forget where, this was, I think, about 3 or something like 2.5 to 3 Tesla field. I don't remember. We just put a bunch of things. So you can see, we're still working on this experimentally. You can see the experimental resolution is not as beautiful as you might like it to be. This is very preliminary experimental data. It's very good. You can sort of see a lot of things, but we'd like to explore it further. It's a good match to begin with. So I should say, in some sense, the primary motive, the quasi-particle decay was a bonus. Our real primary motivation was this fact that in the absence of a transverse field, why the hell is the particle moving? That's something that nobody could explain. So if you look at all the work that was done beforehand, people would just put in some phenomenological SY field and say, oh, and declare victory. But you know, HY is strictly 0, and that's something the experimentalists control. So unless there's some, and there's not a stray fields are not a thing that you expect in those experiments. Once you turn off the experiment, you can expect a misaligned field, but you don't expect a stray field. So it really had to come from some two-body term. And that two-body term was elusive because people weren't sort of taking symmetry very seriously. They were sort of just drawing it as a 1D chain and forgetting the zigzag physics which allows that. So I think the quasi-particle decay to me was actually a bonus, because we were just trying to say, let's just understand the physics at 0 field, and then we can go back to high field later. And so again, the point was that the way people were explaining the decay at high fields was saying, oh, but you know, you have a big field on the system. What if your field was slightly misaligned? Then maybe you have a decay that comes out. So that could explain a decay. But what it doesn't explain is the kinematics don't work out correctly, because that pi shift is really crucial to get the kinematics. The fact that these two quasi-particles, when they decay, have to bounce across the Brillouin zone. The fact that a different way, I showed it in a particular way, but you know, if you actually think about what these kinematics are, it's that momentum isn't a good quantum number, but glide symmetry is a good quantum number. So you can actually do a glide symmetry matching between the two things. So you can ask, how does glide symmetry match? And there, what you see is, with glide symmetry, the Brillouin zone for an even number of particles is pi shifted from the Brillouin zone for an odd number of particles. So you have to sort of jump by pi every time you go from even to odd sectors in the theory. And that's why you're allowed. But the nice thing is, going from the Ising even to Ising odd is also a jump by pi. So you change your, if you like, your Ising parity, but you also bounce to the next Brillouin zone. That fact was really kind of crucial that the symmetry comes in. So there were sort of twofold motivations. But the tricky thing was, once you got the explanation, we were driven crazy. We couldn't understand why the critical point could possibly survive. And we said, okay, maybe it's that there isn't really a critical point. So if you like, this unitary mapping is actually the first proof that there's a critical point, because it's a non-Kramer, so there's no reason for it to be, you know, have a sharp critical. You could always have argued that maybe it's just a sharp crossover. But now we have a microscopic understanding that what's happening is it's really translational breaking that's going on. Or glide breaking, if you like, depending on which language you prefer in this picture.
Let's see. Any questions to Sid from anybody in the audience? Well, I don't see any more hands. Sid, let us all thank you for the wonderful talk.